Air cooling. This is the most common cooling method in any PC build. This cooling technology uses spinning blades or fans that move air through a computer to keep temperatures under control. Mounted on different computer components, fans pull cooler air in and push hot air out, helping other parts to work more efficiently. They don't cool directly, but they maintain the airflow needed to move heat away from vital parts. Fan sizes range from 40 millimeters to over 200 millimeters. Larger fans push more air with less noise, while smaller ones spin faster and tend to be louder. Air cooling with fans is cheap, widely compatible, and easy to install, but without proper planning, they can just move hot air in circles, causing components to overheat or crash. That is why placement matters for this cooling technology. A well-balanced setup, typically with front intake and rear/top exhaust, can dramatically improve thermal performance. Heatsinks. A block of metal that pulls heat away from a component and spreads it out so it can cool down faster. Heatsinks are usually made of aluminum or copper and sit directly on top of a chip like a CPU or GPU. Heat travels from the chip into the heatsink, which has fins to increase surface area and improve cooling efficiency. A fan often blows air across the fins to carry the heat away. Heatsinks are passive cooling devices. They don't move, make noise, or require power, making them reliable and long-lasting. But they rely heavily on good airflow to be effective, and without a fan or proper ventilation, heat can build up quickly. Nevertheless, heat sinks are a core part of most air-cooled systems because they are simple and cost-effective. Liquid cooling. This method uses liquid to absorb heat from components and move it to a radiator, where it's released into the air. A pump pushes coolant through a loop that includes water blocks on the CPU or GPU, tubes, and a radiator with one or more fans. The liquid draws heat away more efficiently than air, making it ideal for high-performance or overclocked PC. There are two main types: custom loops and all-in-one coolers. AIOs are sealed, pre-built systems that are easier to install and maintain, while custom loops offer more control and better performance but are complex and expensive. Liquid cooling runs quieter under load and looks great in a build, but leaks can be disastrous. It's a powerful upgrade, but not without risk. Heat pipes and vapor chambers. These are sealed metal structures that move heat faster than solid metal alone. A heat pipe is a hollow tube with a small amount of liquid inside. When the end near a hot component heats up, the liquid evaporates, travels to the cooler end, and condenses, thereby releasing heat. The liquid then returns via capillary action, repeating the cycle. Vapor chambers work the same way, but spread heat in two dimensions, like a flat plate. Both are extremely efficient at moving heat from hot spots to larger surface areas like heat sinks or radiators. You'll find them in laptops, GPUs, and compact desktop coolers where space is tight but cooling needs are high. They are silent, maintenance-free, and highly effective, but only when paired with good airflow or fans to finish the job. Peltier Cooling. A type of thermoelectric cooling that cools components by forcing heat from one side to the other using an electric current. A Peltier cooling setup includes a flat solid-state device made of two ceramic plates with thermoelectric materials sandwiched in between. When voltage is applied, one side becomes cold, the other hot. The cold side faces the CPU or GPU, while the hot side must be cooled by a heatsink or liquid system before overheating quickly. Peltier cooling can reach sub-ambient temperatures, which sounds great for overclocking, but the downside is that it is highly inefficient, draws more power than it removes, and creates a ton of extra heat. It's rarely seen in everyday builds, but still used in niche setups where silence or temperature control matters more than power draw or simplicity. Phase change cooling. This is refrigeration level cooling for central processing units of computers. A phase change system works like an air conditioner where a compressor pushes refrigerant through a closed loop. The refrigerant evaporates at the cold end, pulling heat from the CPU, then travels to a condenser where it releases that heat and turns back into a liquid. The cycle repeats, cooling as low as -50 degrees Celsius in some setups. It is powerful, silent during cooling, and can handle extreme overclocks, but on the downside, it is big and requires serious insulation to prevent condensation. Plus, it's expensive and often louder than liquid or air systems when active. This cooling method is not for casual builds because setups are rare and over the top, but in raw thermal performance, few methods even come close. Piezoelectric fan. Instead of spinning blades, this method cools using rapid vibration. A piezoelectric fan uses a thin metal disc, bonded to a ceramic strip that flexes when voltage is applied. The motion creates pulses of air that help move heat away from components. It is bladeless and nearly silent, making it ideal for devices where space and noise are concerns. With no motor or bearings, it has low power consumption and high reliability, useful in slim laptops, embedded systems, and fanless designs. However, its cooling capacity is limited. Piezoelectric fans generate less airflow than traditional fans, making them less suitable for high-performance or heat-intensive systems. They're not yet common in desktops, but for compact, low-power devices, this technology offers a clean, efficient solution. Ionic Wind. This is a fanless cooling method that moves air using charged particles. Also known as corona discharge cooling, this method works by applying high voltage to ionized air molecules near a thin electrode. These ions are pulled toward an opposite charge, pushing surrounding air molecules with them and creating a gentle airflow across heated components. The entire process happens without motors or noise, just electric fields guiding air, making it silent and ideal for systems where space is tight or noise isn't an option. However, airflow is limited and requires precise control. While promising, it's not yet practical for high-performance machines, and today, it remains mostly experimental, seen in labs and concept devices. Liquid nitrogen cooling, an extreme cooling method used to push CPUs and GPUs to their physical limits. Liquid nitrogen boils at -196 degrees Celsius, and when poured into a metal pot mounted on a CPU or GPU, it rapidly absorbs heat and evaporates. That drop in temperature allows for massive overclocks far beyond what traditional cooling systems can handle. There are no pumps or radiators, just pure cryogenic liquid and a carefully insulated setup. It's silent, but short-lived because nitrogen boils off and must be constantly refilled. It's risky too, as sudden temperature changes can crack components and condensation can cause shorts if insulation isn't perfect. Liquid nitrogen cooling is strictly for benchmarking and competitive overclocking. It's not practical, it's not safe for daily use, but in raw performance, nothing else comes close. Dry ice cooling. Dry ice offers sub-zero cooling without liquid. Made of solid carbon dioxide, it sublimates at -78.5 degrees Celsius, turning directly from solid to gas. For PC cooling, dry ice is placed into a metal pot on the CPU or GPU, often mixed with a solvent like acetone to improve contact and spread the cold evenly. It enables high overclocks for short durations, similar to liquid nitrogen, but with slightly less cooling power. There's no need for pressure systems or compressors, just careful handling and insulation to prevent condensation and frost buildup. However, like liquid nitrogen, this method isn't for everyday use. The dry ice evaporates quickly, must be constantly replaced, and can crack or damage hardware from thermal stress. Dry ice is practical only for temporary benchmarking and testing, not for long-term system stability. Liquid helium cooling. This is the coldest cooling method ever used in a PC, which could go down to -269 degrees Celsius. Liquid helium is a cryogenic fluid that boils near absolute zero. When poured into a cold pot mounted on a CPU or GPU, it delivers unmatched cooling power, briefly pushing processors to the edge of what silicon can handle. It's used solely for record-breaking overclocking attempts. Even small amounts are expensive, difficult to handle, and evaporate almost instantly. At such extreme temperatures, many chips stop functioning entirely as electrons freeze out of the semiconductor material. There's no practical application here since liquid helium is overkill for any real-world scenario and comes with high risk and zero longevity. But for competitive overclockers chasing world records, it's the final frontier of thermal performance. Liquid immersion cooling. Instead of using air or liquid loops, this approach drops the entire system into a bath of cooling fluid. Components like the motherboard, CPU, and GPU are fully submerged in a non-conductive liquid, often mineral oil or specialized engineered coolants. Heat transfers directly into the fluid, which can either passively absorb it or be circulated to a radiator for active cooling. The result is near-silent operation, excellent thermal stability, and no need for fans or heat sinks. It's used in some data centers and enthusiast builds where cooling density or noise reduction is critical. However, it's messy, expensive, and not beginner-friendly. The liquid can degrade certain materials, and servicing the system is far more complex than with traditional cooling. This is highly effective but rarely practical outside of specialized environments. Thermosyphon Cooling. This system moves heat using phase change and gravity without requiring any pumps. Inside a sealed loop, a liquid sits near the heat source, like a CPU. As the component heats up, the liquid boils and turns into vapor, rising to a condenser or radiator where it cools, condenses, and flows back down to repeat the cycle. It's similar to heat pipes but works on a larger scale and can cool higher power systems. Because there are no moving parts, it's quiet, energy efficient, and highly reliable. Some high-end PCs and servers use thermosyphons to reduce noise and improve longevity, but setup is sensitive to orientation and space. It also lacks active control, meaning performance depends on ambient temperatures and loop design. Thermosyphons offer excellent passive cooling when gravity and design work in your favor. Chip integrated cooling. Instead of cooling from the outside, this method builds cooling directly into the chip. Engineers etch tiny microchannels into the silicon or attach miniature nozzles that shoot coolant directly at the chip's hottest zones. These systems, like microchannel heatsinks and jet impingement cooling, target specific areas where heat is most intense, removing it before it spreads. The approach allows for extreme thermal control and supports future chips with power densities far beyond what standard coolers can handle. It's ideal for data centers, AI accelerators, or future processors that push past traditional limits, but the complexity is high since these systems require precise engineering, exotic coolants, and high pressure flow, making them impractical for everyday PCs. The method is still experimental, but it points to the future of thermal design and high-performance computing. Soft cooling. This reduces heat by controlling how much work the CPU or GPU performs. Instead of relying on hardware like fans or heatsinks, it uses software to scale back performance when full power isn't needed. This includes things like frequency throttling, idle states, or pausing unused processor functions, all of which lower power draw and heat output. It's built into most modern systems, especially laptops and mobile devices, where power efficiency is a priority. It helps maintain lower temperatures without adding noise or extra components. However, it can reduce performance under sustained load, and users may notice slowdowns if thermal thresholds are hit too quickly. Soft cooling works best as a background solution, keeping systems cool and quiet, while extending lifespan and energy efficiency. Undervolting. By reducing the voltage sent to your CPU or GPU, this method cuts down heat and power draw. Every processor is configured with a safety margin, an extra voltage to ensure stability across all systems, but in many cases, that margin is more than necessary. By carefully lowering the voltage, performance can be maintained while generating less heat and extending hardware lifespan. Undervolting is popular in laptops to improve battery life and reduce fan noise, and it's gaining traction in desktops for quiet, efficient builds. Tools like Intel XTU or Ryzen Master make it accessible even for beginners. And that wraps up every major PC cooling method explained. If this helped you understand how your PC stays cool under pressure, give it a like, subscribe for more tech breakdowns, and hit the bell so you don't miss what's next.